Hello class, today I'm going to show you how you can analyze and simulate hyperelastic materials. Let's start with our workbench. Okay, our workbench is ready. This time I'm going to do something different. Instead of starting from the beginning and starting static structural, dragging here, draw the geometry, I'm going to use already started file and saved as WBPZ files. You may ask, what is WBPZ files? They are files which people prefer to save, and it's easier to share, and you can use archive option in the file to create those files. And if the capacity of that file is large, you can clear the mesh information or other unnecessary information. Okay, let's go and open that archive file which is already prepared. So I'm going to restore archive, and I put it in my AP09. So this is my archive file. It says save it. I'm going to save. Okay, so this is our archive. Let's see what material we have. We have standard default structure still here, so nothing special. Let's see geometry. I can open geometry as the old version, design modeler or space claim. It's your choice. For me, both same. Let's go with space claim, as we are usually using space claim. I just want to show you what type of geometry I have decided for this workshop. Okay, it's ready. As you can see, it's a piece of our model, 1/8 of our model. What I'm looking for simulating a dog bone shape, stress and strain testing shape. So usually if you want to find stress strain graph, there are some equipments to find and report those graphs. But for those equipment, you need to generate this dog bone shape of that material and then put it inside, and then they are going to generate stress strain graph, and the early stage is going to be linear. We have Young modulus, which is the slope, and then gradually it is going to tear out. So this is the shape, as you can see here. And I cut this shape to half, and that half another, and use the half of that half, and then I cut the thickness to the half. So I have the current model is 1/8 of the original model. Okay, so we understand the model. Let's open our third section, which is model evaluation. Okay, Okay, it's ready. Let's see what I have. This is my model geometry. I have 3 pieces, and you know why people like to cut it to several pieces and attach to each other, because you could have different mesh quality for the different parts, because this section is going to be important section, and we are focusing on this section than the other two parts. Okay, let's see the connections. We have that connection and the other connection. They are bonded, as you can see here. So basically they're like a one piece. And let me generate the mesh. We could have a much more better mesh. Let me go with fine mesh. Okay, it's okay. And then because I cut this 1, 2, 3 times, so I need to specify frictionless support for the cutting surfaces. The first one is going to be this one, because the thickness is half. The next one, which is this one, it is going to be from here, apply, and the last one is going to be this section. And I want to have 19 millimeter displacement for this side. That is why we selected displacement boundary condition, and let's select the surface, apply that, and I have 19 millimeter of displacement outward. Let's solve it. And we can see the deformation. This side is thinner than the other side, and the other details you can see there. Okay. Now let's close this, because we already know these things, and I'm more interested to hyperelastic materials. To generate a new material, I can start from beginning, or I would like to duplicate this one. Name it, for example, elastomer. And this is created. Okay. Let's check the unit. Unit is millimeter ton, and that one is okay. Now I'm going to add some new properties from the left toolbar. The first one is hyperelastic experimental data. I'm going to have some experimental data, and you know how you can get that experimental data using the equipments we have. Even in our lab we have equipment to get strain stress data for any type of material. So for now I have uniaxial test data include in our property, shear stress, biaxial experimental data, and shear stress. Okay, so I need to fill these 3 types of data. If I click for the first one, uniaxial one, you are going to see we have some tables here which we need to add the experimental data here. So I'm going to right click over this star and import from the table or folder I have. So it should be here, and it is looking for a CSV file, which I don't have it. So it's better, instead of Excel file, to convert our files to CSV. So let me check. So this is biaxial one. This one shear stress. This one is uni. Okay, where were I? So yeah. So this is uniaxial one. Let's go and open my experimental data. For uniaxial one, I'm going to open Excel file. We have two columns, strain and stress. Let's save as, where are you? CSV. Save it. Yes. And don't save it. Anything else? For shear stress one, again, I'm going to go and select CSV file. Yes. No. And for biaxial one, save as. And this one, yes. So now I have CSV files. The first one is uniaxial. Now you can see everything is cool here. But if you select Excel file, usually it shows some symbols instead of numbers. So it's better to go with CSV files. So now you need to take care of the types of the data we are going to have. The first one is strain. Unit is okay. I want to import it. The second one is stress. It should be megapascal. Done. And also I want to import that one. Okay. And you can see the stress strain for this test here. For biaxial test, it's same procedure. Browse. This is biaxial. Let me check if this is the biaxial one or not. Yes, this is the one. Import, strain, stress, done. Another graph for this one. And the last experimental data we have is for shear test. This is the one. Strain, stress, and import both. Here. For hyperelastic materials, we have some models because we don't know how to use these three experimental data to generate those material properties we need for strain, for tension or compression. So there are like a 5-6 different methods to extract those data. Basically what they do, they put all these experimental data in a graph and they fit a curve over it. And using that curve, we have data for all points, not just a few points. Here, for example, we may have like a, how many? 54 points. But if you want to use in ANSYS, it should be like continuous information about material properties. So we need to use some models. As you can see, inside this hyperelastic tab, we have a lot of options and models. I've seen many people using this Muni-Rivlin with different number of parameters. I'm going to use the other one, Yo third order, and right click, including property. By including this model, automatically ANSYS is going to get rid of isotropic elasticity, because by adding this we are going to have hyperelastic materials, and this Young modulus or Poisson ratio is not going to be one number. So ANSYS understands that and says, okay, you are going for the more complex material, so that isotropic elasticity option is not going to be valid anymore. This model comes with 6 coefficients which we need to calculate, and if you have these coefficients, you can the model would be complete, and ANSYS understands the formula extracted from these numbers. But because we have some experimental data, we are going to use and fit some curves for those experimental data and ask ANSYS to generate these 6 parameters out of those fitted curves. So let's right click over curve fitting. As you can see, all those experimental data are here, and I'm going to ask ANSYS to solve curve fit. Done. As you can see, these curves are going to extend more than the range of experimental data. Experimental data, for example, the red one, which is biaxial test data, is up to this here. But this formula and curve is going to continue for longer range. It's not very good one, so let's play with the options. For example, instead of normalized error, I can ask for absolute error and ask ANSYS to fit curve again. This time it's much better, and the fit is better than the previous one. So yeah, let's accept this one, and again right click over curve fitting, and this time say copy calculated values to properties. Now ANSYS is going to extract those coefficients from the fitted curves. As you can see, these numbers are ready. Okay, let's not close this one and go back to model. Okay, yeah, it's loaded. Let's make sure the material properties are well assigned. So I'm going to select all the sections of this one part, and instead of selecting structure still, I'm going to select the elastomer or hyperelastomer material we just created. Okay, now I'm going to go for analysis setting. Let's have 1 second of simulation here. So 1 second is going to be enough, and time stepping, I'm going to, instead of program control, turn it on. We are going to have defined by sub-steps. Let's have 10 initial sub-step, and at least we need to have 5 sub-steps, and the maximum sub-steps can be 50. Usually these numbers can be much larger if you want to have better data. What else? Because this is a rubber and we are going to have a large deflection, ANSYS has a option for that large deflection. As you can see here, large deflection currently is off. Oh, what happened? Here, I'm going to turn it on. If you don't turn this option on, ANSYS is going to create some inaccuracy, and it's better to let ANSYS know this simulation is going to have large deflection. Yeah, I'm happy with this one, and the results are going to be total deformation, stress, and equivalent stress. Let's solve it and let's watch the force convergence. As you can see, up right now we are 50% of the simulation, and then we reach 100%. It was 1 second, so we reached 100% of the simulation, and it converged, and we don't have any bisection, so the object or the geometry we had is performed well. Let's go for deformation. We have about 19 millimeter of deformation, which is almost 2 centimeter of deformation, as you can see here. It's pretty large deformation, and because of this deformation at x direction, the thickness in y direction is decreased, and the shape is a bit elongated. And this is the strain. Highest strain is going to be here, and it's pretty uniform. That is why they designed this shape. When we focus to this area, we have uniform strain. Let's see about stress. Again, stress is very uniform here, and it's a good sign. This dog bone shape is very good shape for this experiment. Okay. Let's create a chart. I'm going to create a chart, and let's see what options we have. Okay, before creating a chart, let me show you how you can create some data which is going to be useful. Okay, let's see. Select a solution, and one of these icons is worksheet. If I click over worksheet, I'm going to see available quantities which I can select as a results. Many data here. I'm looking for stress for x direction, and it is going to be Sx. And right click over it and create user defined result. Done. I have stress as x direction, and this is small user means user defined. I also want to have strain at x direction, because for this test, let me go back. For this test, everything is going to be x direction. The reason of creating this dog bone shape is to have one directional stress or strain. That is why I'm going to generate stress and strain at x directions. If you go down, you are going to see strain at x direction is going to be EPELX. So let's create the user defined strain at x direction too and solve them. So these are going to be stress at x direction 2.6 megapascal, and strain 0.5 millimeter, the maximum strain, which is for this side. Okay, now let's draw a chart. Where are you? Here. To draw this chart, as you can see, we have outline selection. I'm going to select these two user defined, which is stress and strain results. Let me select it again. So I have these two objects selected, and I'm going to apply here. So outline selections are going to be those two objects or results I as a user defined results I generated. So stress as extraction, strain at extraction. What I'm looking for? I'm looking for stress strain graph. So let's see. For x-axis, let's have strain, and linear, it's okay. It's not bad to have some guidelines. For x direction, it is going to be strain, and unit is going to be millimeter over millimeter. And for stress, definitely it is megapascal. These are the labels I add, and then I don't want to have any time variable here. Oh, what else? This is my x-axis and this is my y-axis. I want to omit the other two. So let's see the result here. This is my stress strain graph. As you can see, linear up to here, and then gradually we have increasing stress. Okay, so this stress and strain graph is for 19 millimeter displacement. What if I increase this to, for example, 50? Let's see what is the effect. Okay, let's see. Our calculation converged. We don't have any problem about getting bisection, and everything is okay. So let's go back to the deformation. Now you can see deformation is much larger and up to 50, which is we selected. Strain is higher and stress increase up to 16. The previous one was about 2 megapascal. Now it's 16. Directional one, this is the directional stress in x direction, and this one is directional strain at x direction. And we can't see any problem with it. Okay, so if I increase this one much higher, for example 100, we are definitely going to see bisection occurring during our loading. So it's okay up to now. We reach 50%. Now, yeah, the red line is bisection occurring here. And it was about above 50%. When we reached 50% of full load, we had this bisection happened. So we need to decrease this displacement for the dog bone to not have a bisection. Okay, it's enough for this workshop. The next one is going to be again elastic materials, but different type.